Greetings, everybody. So we are continuing our videos on chaos-based image encryption. And the topic of today is a question about permutation. Okay, is permutation enough to encrypt an image signal? Okay, and this is what we're going to answer. Let me remind everybody that we are talking about symmetric encryption here. This means that on the transmitter, we are using a chaotic system to encrypt some sort of information. Let's say it's an image, safely transmitted through a public channel. And then at the receiver end, the receiver should have the same chaotic system with the same configurations, so initial conditions and parameters. And they can reverse the process, decrypt the signal, and obtain the original information signal back. And that's why we're talking about symmetric encryption. And the most common options and actions are permutation and substitution. Okay, permutation basically means shuffling the image pixels to disperse the information throughout the image. And substitution, which is a secondary action, means taking each pixel value and replacing it with another one. So a very simple question rises here. Is shuffling enough to encrypt the information? This is a very logical argument because if you see the three images right here, one might say that, okay, the first image depicts some sort of information, but once I shuffle the pixels throughout, this image to the naked eye becomes meaningless. So when I look at the shuffled image, I cannot understand any type of information from it. I cannot derive any information from the original image. So why go into the second step and encrypt it further? I mean, isn't this enough? So this is a very logical argument, but there are very simple answers to that and explain why this isn't enough. So although to the naked eye, the shuffled image looks very secure and encrypted, under some specific statistical tests, this shuffled image fails to hide all the possible information about the plain text. So we discussed a little bit about this on previous videos. So let's see it again. First of all, the classic statistical test is the histogram. Okay, it depicts the distribution of grayscale values in an image. So naturally, if you think about it, when we permute and shuffle the pixels of the image, we cannot change the histogram. Okay, simply put, if a specific gray value appears n times in the original image, after shuffling, it still appears n times. So the histogram doesn't change. Okay. If you look at the image right here, for example, you will see that on the upper scale, around 255, we don't have any very, very white pixels. Okay, so after shuffling, the same thing holds. We don't have any white pixels in the shuffled image. So you see that although to the naked eye, this image makes no sense, really under the histogram analysis, it reveals a lot of information. For example, an uneven distribution of pixels. So this is a clear understanding that despite not making any sense to the eye, under specific statistical tests, the results are very vulnerable. And that's why we need to go into the second effort of further encrypting the image. Okay, so this is why permutations fails if it is as a standalone action for the histogram analysis. And we have another example of failure here, which is the entropy test. As we mentioned, entropy, which measures some predictability, is computed over the image as a whole. So whether you shuffle the pixels or you don't shuffle them, does not affect the entropy value of the whole image. And this is why, again, this is a test that fails. The original and shuffled images have the same amount of entropy, right? So again, this is a secondary test which fails if we only consider permutation of the signal, okay, of the image, sorry. So two of these tests fail, okay? Of course, the shuffling has another very, very, very good effect on the image, which is that it greatly protects it against cropping attacks. So where some information is lost, if we have previously shuffled the pixels, it really helps us in obtaining some information back from the cropped part. Okay, but there is also another issue with permutation. Okay, regarding the cropping attacks, I'm going to talk about another video. But finally, let's also discuss this simple situation where permutation fails. Let's say we have an image that has only a single color throughout. Okay, let's say it's all black, but any value will be the same. What will happen if we shuffle this image, right? Nothing happens. because all the pixels have the exact same value, right? So even after shuffling, the image remains entirely the same. Okay, so this sort of images are completely unchanged by the shuffling effect. Okay, and this is why we need to have a second step, which is a substitution step, in order to fully encrypt this image. Okay, so this is another very clear example that, you know, if you have an image that has only one color in it, shuffling has absolutely no effect. Okay, so you see that only permutation is not enough to guarantee encryption and full security. Okay, regardless of the fact that the image may not make any sense to the naked eye, it's still vulnerable. Then that's why we need to have a second step, much more important, which is the substitution step. Okay, so this is it for our video, and we're gonna see you again in the next video.